In this video, we're going to talk about finding volume using specifically the disk method. We can use the disk method to rotate about either the x-axis or the y-axis, right? So in this example, we're going to be talking about the x-axis rotation. So as we previously said, volume is the integral of area. And so in this situation, we're going to define that area as being pi r squared. And we're using this capital R here. So capital R is just the radius of that disk. All right. So in the previous example, all of those area regions we were adding up were circles or disks. So this is just kind of a simplifying way of saying the same definition. All right. So let's look at a problem. So we're going to find the volume of the solid using a disk method, which is generated by revolving this shaded region here about the x-axis. So that's a rotation about this axis. All right, so if we take that shaded region and rotate it about the x-axis, we would get kind of this double-ended parabolic shape, right? But we have all these different disks or circles inside that are created when we do that, right? So we think about all those circles that are created here. So lots of disks, and essentially what we're going to do is we're going to define the radius as the function, and we're going to integrate it across our bounds, which would be in this case 0 to pi over 2. All right, so my function, right, y equals sine of x cosine x. So the function represents the radius of this shaded region. I'll draw that back in there, right? My radius is from the center out to the edge, and the function is that bounding edge. So this is going to be my capital R of x, right? So volume is the integral from a to b, and a and b are my bounds 0 and pi over 2. So we have 0 and pi over 2. Pi times sine of x cosine x quantity squared dx. So that is our setup for getting this volume if we rotate this guy about the x-axis. So now we just need to solve the integral. So let's begin working through this problem. One thing I'll do is I'll go ahead and pull that pi out in front. Got the integral from 0 to pi over 2 of sine x times cosine x quantity squared. And of course I could write that as sine squared times cosine squared, but I don't know how to deal with that readily. So this is where we might resort, I should say, to using some of our trig identities. I do know I have a sine double angle. Sine 2x is 2 sine x cosine x. And if I divide by 2 there, I have sine x times cosine x would equal, I have sine of 2x divided by 2. And of course that is quantity squared. So this 2 squared, I'm going to pull that out in front. I have pi over 4, the integral of from 0 to pi over 2 of sine 2x quantity squared dx. Now at this point we use a u substitution. I'm going to let u equal 2x. So we'll say let u equal 2x. And what that gives me is that the derivative of u with respect to x, 2, or rather 1/2 du equals dx. So what does that look like? We now have pi over 4. My integral, my bounds are going to need to change. I have sine of u quantity squared, and then my dx becomes 1/2 du. That 1/2 is going to come out in front and become an 8 here shortly. And when I look at changing my bounds, I'm plugging them into my u equation. So 2 times 0, that would remain 0, but 2 times pi over 2, that's going to give me this bound of pi. So remember, if you do a u substitution with a definite integral, you need to make sure that you change or mend your bounds. So now we have pi over 8 from 0 to pi of sine squared u du. All right, so here we end up actually having to put in another substitution. I don't like to integrate trig functions when they're squared, so we always try to reduce them. And one that we use a lot would be sine squared u equals 1 minus cosine of 2u over 2. That's one of my double angle identities rearranged. So I'll make that substitution, and this is just a direct substitution here. I'm not changing any variables. So I now have 1/2 minus the 1/2 of cosine 2u du. So this is now equal to that. I can put parentheses around it if we'd like. So continuing to work through this, I'm going to pull that 1/2 out. I've got pi over 16, the integral from 0 to pi of 1 minus the cosine of 2u du. And now each of these terms is easily integrable. So I've got pi over 16, the integral of 1 becomes u, and the integral of cosine 2u is going to become sine of 2u over 2. And this would need to be evaluated from pi to 0. So I'll plug in pi first. That'll give me pi minus sine of 2 pi over 2. Sine of 2 pi is, of course, 0. And then I will plug 0 in. That gives me 0. Sine of 0 over 2 is going to be 0. So all of those are going to end up canceling out, but I'll work that out for us right here. So let's see. I have pi over 16, and that would be pi minus the sine of 2 pi over 2. And then we would have minus 0 minus the sine of 2 times 0 over 2. And as we've just said, sine of 2 pi is 0, minus 0, sine of 0 is 0. We're going to end up with an answer here, pi squared over 16. Because we just have pi left in the parentheses, pi squared divided by 16. So that's how we use the disk method. I'm going to do another example now, and we'll talk about finding the volume of a solid rotated about the y-axis. And that will be in the following video.